Today we want to talk about mechanisms of strengthening, which basically means how do materials get stronger, especially metals. So let's dive in. When we talk about strengthening of materials, we are talking about plastic region or beyond plastic region. So on a stress strain curve, we are here and beyond. So we are in the plastic region, and when we are talking about strengthening, we are referring to plastic deformation and how materials do get stronger when you apply strain on them. As you can see here on the stress strain curve, when we start here, and that's our yield strength, which we begin the plastic deformation, as we apply more strain, our material is getting stronger, stronger, and stronger, of course, up to a certain point that we discuss in other videos that what necking means. But anyway, from this point to that point, when we are applying more strain, you see that the material is obviously getting stronger. So the stress to move the material further, to further deform it, becomes more and more. It means that our material is becoming stronger. So how to understand this and how to know what factors affect this strengthening mechanism of how these materials are becoming stronger. So we know what makes materials strong, and we know how to make our material of our interest stronger. For example, we have a block of aluminium and it has a certain strain. In this course, we want to understand what can be done to this block of aluminium so we can make this block stronger, okay? And so what mechanisms are involved? And we are discussing mostly about plastic strength, not elastic strength, okay? That's why we are in plastic deformation. So when we are in plastic deformation, we immediately call dislocations in. At the beginning of plastic deformation, as we discussed also before, always it begins with movement of dislocations. And these dislocations, as we discussed last time, these dislocations are these half planes that we have here. This is our half plane. These dislocations are these half planes, which we call line defect. And at the beginning of the plastic region, these dislocations begin to move. And the movement of these dislocations is responsible for plastic deformation. In another word, these dislocations accommodate plastic deformation. So they allow for plastic deformation and further strain to happen. This kind of movement and mobility. So I'll bring the video also here one more time for us to check out to see how dislocations move. So at the beginning of plastic deformation, when we are applying stress, these lines, these black lines that you see now, that they are moving, these are dislocations, these half extra planes that are moving. If the material for this course is sounding a bit too much for you, because probably you haven't followed our previous video, so I'll put the card up and also into the description to follow there. So these are the movement of dislocations, these black lines that are moving. Also in this video, you can also see these dislocations, these extra half lines begin to move, which are responsible for plastic deformation. We need the movement of these dislocations for the plastic deformation, for bending of a metal to take place. Without their assistance, we cannot perform that much plastic deformation. We cannot apply it to our materials. So they are really important. But dislocations, they have a kind of a double-sided effect. Dislocations, well, they assist plastic deformation. So without them, the plastic deformation would not happen that much and your material becomes brittle and it happens early. So if we look at this stress strain curve, because we have now dislocations and dislocations are moving, we can apply more strain, and this is our strain, right? So we can apply more and more strain because these locations, in this case, can move, okay? But on the other hand, the same dislocations that are allowing us to bend the metal even more, The same dislocations are also responsible for this metal bar that we are trying to bend to become stronger as we apply strain, as we try to bend it. So yes, we can bend it more, but the same dislocations are responsible for this metal to become stronger as you're applying stress. So you see, it's becoming stronger and stronger. Why it's happening? Because these dislocation line, as they are moving, they will bump into each other, pin each other down, and the further movement of these dislocations, which are responsible for further strain, will be harder. So you need to apply more force to push them forward or to push them around to have more strain, to bend the metal even more. So dislocations, yes, they allow us to apply strain to bend the metal really by a lot. If we don't have these dislocations, if we have a few of them, then you cannot bend more. It means that your material becomes brittle. You cannot apply this much strain until it fractures. Probably it fractures somewhere here. Okay, so we need those dislocations, but the same dislocations as they move, and because they bump into each other and they slow each other down, you need more force to push them forward. Therefore, you will feel that your material has become stronger. It means that as you're bending your metal is becoming stronger. And by bending, we mean strain, therefore it's strain hardening. So, and also here you will see an equation for the relationship of dislocation density, how much dislocations we have, and how these density of dislocations, like how much of them are concentrated in a certain area, is responsible for to make our material stronger. So if you have this, if you look at this equation, what is important for us are these values. So this is our dislocation density. This is our dislocation density, and this is our strength or yield strength, considering that there are no additional dislocations. So if you imagine that there are no additional dislocations introduced to our system, to our material, uh, then this would be your yield strength, sigma 0. But now look at, according to this, when we increase the density of dislocations, this value, then our new yield strength, which these additional dislocations will be even more than sigma 0. So if you want to plot that, if we have sigma here, which is our yield strength, if in case we have additional dislocations, and then here what we can put in here, we can put the density, the square root of the density of dislocations. Therefore, we would have a straight line, and the slope of this line will be this value, right? For the moment, we don't care what those value means. We are now looking at the relationship between density of dislocations, this one, and the yield strength. So if this one is 0, then your yield strength, according to this, it says that then your new yield strength will be equal to the yield strength without any additional dislocations. Okay, and it says as you increase the amount of dislocations, the density of dislocations, then your strength, your yield strength will go up. And our yield strength is here. And as we said, when you apply plastic deformation, these dislocations, they move and bump into each other. Also, when you're applying strain, you generate more dislocations. So your dislocations are increasing the amount, the density, and they will also pin down even more dislocations. So this, as you see that this relationship, that by increasing the dislocation density, you're increasing your strength. You can see it also here in this stress strain curve, that from here, as the amount of dislocations are being increased, then the strength is also increased, right? So that's a relationship between your dislocation density and the strength of your material. But there's one problem with this equation. The problem is it tells you that if the amount of additional dislocations is zero, then your new yield strength will equal to the strength of your material, considering that there are no additional dislocations, which is in this place. That is lower than your new yield strength, right? It's lower than this. Well, that's not true. Because as I said, they have a double-sided effect, these dislocations. If you have very few dislocations, actually your material becomes stronger. The yield strength will go even higher. So for little amount of dislocations, this formula does not hold. So because dislocations are responsible to accommodate plastic deformation, if you have a limited amount of them, then the plastic deformation cannot happen that easily. Therefore, your material becomes much stronger because there are no dislocations to accommodate for plastic deformation. Therefore, your yield strength will become much higher than what you have, considering that you have this dislocations available. So this formula, you apply it only when you have, let's say, enough amount of dislocations. If a material is considered with zero amount of dislocations, then this formula does not hold. Usually materials that do not have dislocations or have a minimum amount, they're so strong, they could be 10 times stronger. For example, you have a block of aluminium and the yield strength of that block of aluminium with normal amount of dislocations, it's 60 megapascal, for example. If you minimize the amount of dislocations within that block of aluminium so much, then the yield strength could go up to 1 to 2 gigapascals even. Okay? So dislocations on one part are responsible for plastic deformation when they start to move. As you apply strain, you generate more dislocations. And according to this formula, as the density of dislocations are increased because they bump into each other and slow each other down, therefore you need more force to push your material even more, to bend it even more, and your material will become stronger. You see it here and you see it here. One problem with this formula is that when the amount of dislocation is zero or approaching zero, the density of dislocations, then your strength, your yield strength will be equal to sigma zero, which is actually a lower value, but that's not true. When you have minimum amount of dislocation, your sigma y, your new yield strength, will become much higher than this. So you can only use this equation for when you have some amount of dislocation. Otherwise, you cannot use it because materials with minimum amount of dislocation, they have a very high yield strength, okay? So that's one way of strengthening. It has to do with the movement of dislocations. Actually, all the mechanisms of strengthening, they have something to do with the movement of dislocation. So whenever you're asked or you're pondering yourself about making, especially a metal, stronger, you always need to think about the movement and mobility of this dislocation. Any mechanism that can hinder or slow down or pin down the movement of these dislocations in the plastic region would make your material stronger. And we know how it makes it, and we kind of know the equation why and how the density of dislocations will contribute to the total strength of your material. So what else we can do to pin down this, or what else we can do to pin down these dislocations? Because as we said, when you start the plastic deformation, you're also generating dislocations, and that's the natural way of increasing the density of dislocations here. So therefore, your strength also goes up. But what else we can do to kind of mess with this dislocation so our material becomes stronger? One additional way to do that is to mess with the grain size. If you alter the grain size, it will affect the movement of dislocations, and also therefore it affects your strength. How? So in previous video, we showed this structure, this microstructure, that we have certain grains, and within these grains, we have these atomic planes and dislocations. The line dislocation lines also are here, right? Within each grain or crystal, we have dislocation. So now look at this. If you have a very large grain, like this grain that I'm now putting border on, if you have a very large grain and you start to apply plastic deformation, then this dislocation has distance to move to reach to the grain boundaries. Therefore, then it will be stopped by the, for example, grain boundaries. But when you have a smaller grain, then these dislocations have a very little amount of distance to move to reach to a grain boundary to be stopped or slowed down by a grain boundary. Therefore, it tells us that large grains provide more space for dislocation movement as compared to smaller grains. Okay, and then we can also, change the grain size of our material. So it shows us that for the same block of aluminium that we have in our hand, if in the block of aluminium we use very rough and large grains, then it would be softer relative to an aluminium with extremely tiny grains, because it doesn't allow doesn't give a lot of room for dislocations to move the small grains. So as we reduce the size of the grains, we are making our material stronger. Why we are doing that? It again has to do with dislocation. So all the strengthening mechanisms, most of them have to do with the movement of these dislocations. So grain size is also one of them. So as you make the grains smaller, you are limiting the movement of these dislocations. Therefore, you are making your material stronger. So the smaller the grain size, the stronger the material. And that's kind of a formula that we can use to that to kind of understand that. So here, D is your grain size. D is your grain size. And now we make D infinite, okay? So if we make D infinite, then this will become 0. Grain size, infinite grain size means a single crystal, means a crystal that only has one grain. What kind of crystal that has only one grain is a single crystal? So if the grains is large enough, it means that we have only one grain. So we don't have multiple grains like you see here on the image on the right. There is a polycrystalline, but when you approach this grain size into infinite, it means that you only have one grain, so it's a single crystal. So if it's a single crystal, your yield strength equals to your natural yield strength of your material. But when it's a polycrystal, and then you have some certain grain size, because of the reverse relationship, it is telling us that the larger the grain size, the smaller your yield strength for polycrystalline material. So if you have single crystal, then your yield strength is equals to the natural, resistance of your material for plastic deformation, which is your natural yield strength. But if you have a polycrystalline material, the smaller the grain size, the stronger your material. And that's the reverse relationship that you see here. When you're comparing yield strength to the grain size. So that's also one way of strengthening your material. That's one of the ways that you can limit the movement of these dislocations by making the grains smaller. Therefore, you're limiting the movement of dislocations. So as I said, any other method can be used to pin down these dislocations. Also making alloys and composites can, in a way, limit the movement of this dislocation. So I want you that whenever you're thinking about making your metal stronger, which are strengthening it, you always bring in dislocations and you think within that framework, how do I stop them, slow them down, and limit them? For example, adding ceramic particles to your metal can make your metal stronger. How it makes it stronger? For example, in this picture, we have a metal matrix composite. Image on the left is our metal. It's just metal particles, and image on the right is metal particles mixed with ceramic particles. The bright particles here are ceramic particles, and this material would be stronger than our metal. In what way? Because these ceramic particles, we again need to think within the framework of dislocations. So how this metal matrix composite, which is reinforced with ceramic particles, how this could be stronger than our metal? One way is that because we have ceramic particles embedded within the metal matrix, these ceramic particles would act as a barrier towards the movement of dislocations again. So if they are acting as a barrier to move towards the movement of dislocation, then adding ceramics to a metal and making a metal matrix composite can make our metal even stronger because it's limiting the movement of dislocations again. So one important key, always think about within the framework of movement of dislocations when you're thinking about the strengthening of your metal. Whatever that you're doing to your metal, if you're wondering if it makes it stronger or softer, think about the movement and mobility of dislocations. And that's most of the fundamental that you need to be thinking and analyzing strengthening of materials. I hope you learned something today. I see you next time.